All right, welcome back for another episode of Connie 352. Today, we're going to be discussing pumps and pumping systems. Specifically, we're going to be discussing the primary-secondary pumping method. Now, normally I would draw this on the board in class, and I tried doing a test run of that using an iPad and drawing it as I went, and it just looked even worse than it normally would when I drew things on the whiteboard. So I just didn't like it. So what I did is I created a PowerPoint slide here that kind of shows the pumping systems. And what I hope is that this will be a little bit easier to follow than if I was to try to draw it by hand as I went. Now, I uploaded this on Tuesday originally, and then today's Wednesday, so I uploaded a new version. I added some stuff to it. So if you're watching this and if you upload it, just make sure that if it doesn't match what you have, make sure you've uploaded the most recent copy, because I have revised it. At first I did it, and then I decided to add to it, and then I decided to add to it again. So it's a work in progress. This is new experience for me. So let's talk about pumps and hydronic systems. Hydronic systems, those of you that are going into mechanical design perhaps, or into mechanical contracting, something to keep in mind that I swear hydronic system understanding and design is kind of a lost art. I don't think that just fluids does not teach you what you need to know. And I kind of think that our university setting focuses a lot on components rather than systems. In other words, they'll give you entire classes on how to design perhaps a heat exchanger, or how to calculate the friction flow in a pipe. But in terms of putting the pieces and parts together and making it all work, that's a little bit more difficult. So we're going to go over basics, and I do mean basics today. So let's go over the basics of a hydronic system. Specifically, we're going to talk about boiler systems, but all the same thing applies to chiller systems. And the drawing that I have here is pretty simplified. This is like a basic, I've got a boiler, I've got a one load at the end of it, somewhere, and then we use one pump. So when the boiler is on, the pump comes on, it pumps 100% of the water needed all the way to wherever that coil is. And then once it gets there, it goes through that graphic there above coil number 1 is a three-way valve. Here, let me show you what a three-way valve is. Right? This is a three-way valve. One inlet and two outlets. Right? It's called three ways because there's three locations that you can hook pipes up to. In other words, water, when it comes in, one of those could either go to either the outlets. It just depends on the position of the valve operator inside of there. Now, we don't need to get into the specifics of how that works, but the whole point is that if we look at our flow diagram here, that valve can either send hot water to the coil or around the coil, and then it goes all the way back to the pump, to the boiler, and around it goes. Now, this is a very simplified version of control. This would have been what was done, say, 70s and 80s and before that, when piping systems were very simple and we didn't worry all that much about energy efficiency. In other words, the control systems were simple. You turn the boiler on, you turn the pump on. Pump circulated water to that coil, whether it needed it or not. And if it didn't need it, that valve bypassed the hot water around the coil, and it came back, and that water wasn't used. In other words, if we made this water at 180 degrees Fahrenheit, which was very, very common for boiler systems, then it came back at 180 degrees Fahrenheit because it wasn't used. And the only loss that we would have is any loss along the way, maybe some loss through the pipe wall. Very, very simple and very reliable. I mean, it worked, except one, we are using a lot of pump energy just to pump it all the way out to the coil if it's not used. Let's take an example building. Let's use Merle Hay Mall. I used to be their engineer and review all their systems, and they originally had a system like this when the mall was built. In other words, they pumped all the water needed all of the time. And think about how large of a building Merle Hay Mall is. The distance from the boiler all the way out to the most remote tenant space or coil, right? Every tenant space is going to have a heating coil in it. That could be hundreds and hundreds of feet. I think for some of them, it's probably like a quarter mile, almost a half mile distance. So you're spending a lot of energy to pump water that you really didn't need, and then you bypass around and you come all the way back. So this wasn't a terribly efficient system, but there wasn't any other choice really. Now, how much water do we need? Here, I'm going to go over the calculation. The equation for heat transfer in and out of water is Q equals 500 gallons per minute times the delta T. The delta T being the difference between the hot water inlet and the hot water outlet. All right. Those of you that are taking some other mechanical engineering, you know that there's something like, usually this equation has to do with specific gravity of the fluid, density of the fluid, a few other constants in there, speed of light squared. No, just kidding. That's not in there. All right. But it's a much more complicated equation. This 500 is a constant that makes everything else work out, the gallons per minute and delta T. As long as you have Q in BTU per hour and the delta T in degrees Fahrenheit and the gallons and the flow rate in gallons per minute, this 500 constant just makes everything work out neat. Now, what we need to calculate is if I have a boiler and if this boiler has a certain output capacity, how much flow rate are we going to need? Now, the difference in temperature between the heating water supply and heating water return, that is normally a designer's choice. Kind of like supply air temperature for air conditioning systems, the delta T from heating water supply to heating water return is usually designer's choice. Common delta T's between supply and return are like 20 degrees, probably no more than 40 degrees. In my personal experience, I like to use a 20 degree delta T. So that's what we're going to use for these examples. It could be something different in other systems, but for my examples today, I'm going to use a delta T of 20 degrees. Now, the real question is, what is your heating water supply temperature and what is your heating water return temperature? Now, when we talked about condensing appliances and condensing equipment like boilers, we learned that the cooler the heating water return temperature is, the more efficient the boiler is. And you need a heating water return temperature down around less than 120 degrees to get that boiler to start condensing and to operating at the really higher efficiency. Boiler efficiency varies with return water temperature. However, don't supply really cool return water to a boiler if it can't handle condensing. In other words, if the interior of that boiler isn't made out of stainless steel and it isn't meant to see condensing, don't do it. If you go into a lot of buildings, a lot of older boilers will use something like 180 supply and 160 return. That's fairly common, and that's what I've used for my for my examples today. All right. So knowing this, if we know the boiler efficiency and we know the delta T, my example here is let's just use a 20 degree delta T and a 90% efficient boiler. Okay. So we take 1 million, let's assume the boiler input is at 1 million BTU per hour. For your final project, you might use a different input capacity on the boiler. All right. You can use whatever boiler that you want. I gave you in the handout for the problem statement, I gave you some vendors that you can use. You can use any one of them. They produce a whole wide range of boiler capacities. So use whichever one you want. But what I do want you to do is when you're calculating your flow rate for your boiler, I need you to tell me what your input capacity is. I need to tell me what the efficiency of that boiler is. Do not make up an efficiency. I want you to tell me what is your heating water return temperature and what is the efficiency of that boiler at that point. All of the boiler vendors will have efficiency curves so that you can just look that value up. All right, so I want a copy of that output, and I want you to show me what this efficiency is. And then I want you to calculate for your given boiler, what is the flow rate that it needs to have? In other words, how much hot water do I need to pump in gallons per minute through that boiler to make it work? Now, looking back to this simple one, this is too simple. This is just a basic illustration. In reality, boiler plants are going to look more like this, where I have multiple boilers and multiple loads. I only put 4 coils on here, but for the Merle Hay Mall example, in Merle Hay Mall, they have 100 stores, 150 stores, something like that. So we might have hundreds of coils that we're supplying to. I only put 4 to make the diagram easy. So the way this would work is we would have one pump with the boiler. Its only purpose is to pump water through the boiler to make up for the pressure loss of the water flowing through the boiler. That's it. So this pump will pump 100% of the water that this boiler needs. This pump, pump 2, will pump 100% of the water that this boiler needs. And then pump 3, the main distribution pump, will pump all of this water as far as it's needed out to the coils. So let's use our million BTU per hour input with a 90% efficient boiler. That means pump 1 is pumping 90 gallons per minute. Pump 2 is pumping 90 gallons a minute. And then pump 3 is pumping 180 gallons a minute all the way out to the coils. The 3-way valves can either send water through the coil or around it and then all the way back. Like I said, the distance that pump 3 might have to pump could be miles. Who knows? In a large building. So the question is, how could we make this better and more energy efficient? Because to be perfectly honest, we are using up a whole lot of energy in that distribution pump for not much purpose. I mean, how often is a boiler plant going to be at 100% load? Kind of reviewing and looking back at our examples, we know that, from our calculations, we know that we may calculate it for worst case situations, but that might only happen a few hours in any given year. Maybe some years it won't happen at all. So the point is that the vast majority of the time that this building is operating, we're going to be pumping all of this boiler water, and rarely would we ever need all of it. So let's talk about a system that does a little bit better job of this and gives us a little bit more energy efficiency. All right, and that's where we come to the primary, secondary pumping system. Now, if you don't have this, what I would suggest is if you have the chance, maybe print this off and get ready to take a few notes as we go through. or maybe sketch this off on a piece of paper where follow along, because I really want you to understand the primary, secondary pumping and the idea of a bypass line. Notice we added something here, right? We put in a pipe that goes directly from the supply pipe to the return pipe. And then we also added a variable frequency drive, right back here. We add a variable frequency drive onto the main distribution pump. Something else that we changed is we got rid of those three-way valves and used two-way valves, right? Here's an image of a two-way valve. Here we go. There's a two-way valve. In other words, there's only one way in and one way out. Two ways to connect pipes to this valve. All right, there's all sorts of different examples here. Back to there's a three-way valve, the one on the left, and the two-way valve is the one on the right. Here is a very small two-way valve, right, like you might find on an individual fin tube unit, or maybe a small terminal air box. This one and this one, these are both small sizes. That pipe happens to be 3/4 inch diameter. In other words, it's pretty small stuff. This one with the flanges, all right, those are much larger. Those might be 6, 8, 10 inch, and maybe even larger pumps. And the reason I know that is that if you look here, it's really hard to see most likely on your screen, but there's actually bolt patterns so that you can bolt a flange to this thing. All right, so you might see them very large, they might be very small, they all work the same. In other words, that controller varies the amount of water that can go through that valve. So that, back to our flow diagram, only as much water goes through each of those coils as is necessary. So let's say that it starts to get cold, the temperature goes down, we need some heat in the spaces. Each of those two-way valves start to open up. The pressure in this hot heating water supply pipe goes down. So our variable frequency drive on our distribution pump speeds up. It pumps more water from the boiler plant down this long distance and through these coils. Everything else, whatever that variable frequency drive isn't pumping, everything else goes through this bypass line. And here, just let me talk about this bypass line for a second. When you see this bypass line in the field, it'll look really weird. It'll look like all of the water that this pump is pushing through the boilers, pump 1 and pump 2 is pushing through boiler 1, boiler 2, should go right back here like this. I know that's what it looks like. However, done properly, understand this, pump 3 is much more powerful than pumps 1 and pump 2. And as it speeds up, it is going to pull all of that water that these two push through the boilers down that long distance and back. Right? And then once the water gets back here, it's going to go into the suction of these two pumps and go through here. And then once we get the water here, as much as is needed is going to go through pump P3. By sizing pump P3 properly, we can force as much water as we want through the load side, and that is called the secondary side. The boiler side of this line is the primary side. The load side of this pipe is the secondary side. So these are the primary pumps, and that is the secondary pump. Usually, pump P1 and pump P2 are relatively small because all they have to do is make up for the pressure loss of pumping the water through the boiler. These are probably fractional horsepower pumps, probably something mounted in line. They're not that big. They are also traditionally constant volume. In other words, when the boiler comes on, the associated pump comes on, and that's it. It's either on or it's off. Pump P3, the distribution pump, is normally much, much larger compared to pump P1 and pump P2. In other words, if pump P1 and P2 are like 1 horsepower or less each, pump P3 might be 50 horsepower, 100 horsepower, much, much larger. And as that pump speeds up and slows down, it's going to take as much water as it needs from the primary side and pump it all the way out to those loads, the coils that are distributed throughout the building. All right. Now, here, I want to illustrate this with some temperatures and some flow rates to really help you understand how this works. All right, let's say that we are operating at a fractional load. In other words, we only need half of the output from one of these boilers. Let's say these boilers are exactly the same size. That would mean that we need 25% of the total capability of our boiler plant, which is half of one of the boilers. So our VFD will be operating at 25% speed. If these boilers are producing water at 180 degrees Fahrenheit, one of the boilers is on and one of the boilers is off. So there's no water flowing through boiler 2. And 100% of the design capacity of boiler 1, remember, that's 90 gallons a minute, is going through boiler 1. But we only need 45 gallons a minute downstream. So the VFD is at 25% speed, moving 45 gallons a minute down there. That means 45 gallons a minute goes that way, and 45 gallons a minute comes through this bypass line and back through pump P1. Well, what happens to the temperatures? The heating water supply is a constant 180 degrees. That should always be a constant. If the boilers are sized properly, their controls are going to keep the outlet temperature at 180 degrees. All right, as soon as it gets out to the coils, if it's going through a coil, that means that it's needed. In other words, it's transferring energy from that heating water supply into the space so that water, after it comes through the coil and comes back, it has been used. We have taken energy out of it. So it has gotten cooler. It's been cooled down to, and in our example, I'm using a 20 degree delta T, it has been cooled down 160 degrees. When it comes back to the boiler plant, this is at 160, this is still at 180. If these flow rates are still the same, they're going to mix, and 160 is going to mix with 180 in a 50-50 mix, and we're going to get 170 degrees Fahrenheit back here. Well, what happens if space temperatures continue to get cooler and we have an increased demand for heat? The VFD is going to speed up past 25%. It's going to speed up and it's going to speed up and it's going to keep on going to maintain the space temperature where we want it to be. At some point, that VFD is going to reach half speed. In other words, I'm using 100% of the boiler water that boiler 1 can produce at 180 degrees. We're using 100% of it, and it's all coming back at 160 degrees Fahrenheit. Well, if I reach 160 degrees Fahrenheit, that tells us something important about the plant. It tells us that boiler 1 is using or is producing all that it can, and we're about to start needing more. So what will happen is that we need to bring on boiler number 2, bring it online. Let's say we bring boiler 2 online. We instantly switch it on. Now both of these, now pump P2 comes on, and we have 100% of the water of both of these coming, but yet the system is only using half of it still. Half of the total. So this coming back at 160, the return water temperature once again drops down to 170. Well, what happens as we continue to increase demand? Let's increase the demand up to 100%. If we got to 100% on the VFD, both boilers are on, the heating water return temperature should drop to 160, and now we are delivering the maximum capacity that this system can deliver. All right. Now, what did this primary, secondary system get us? Well, in all honesty, how much time are we going to spend at 100% flow on that VFD? If this is a large 100 horsepower motor, that's a lot of energy, but we are rarely going to need 100% of that pumping capacity. Let's go back down to 50% capacity. Remember, what did we say about the relationship on a VFD has between flow and power consumed? Remember, half speed is half flow, but half speed is also 1/8 of the power. Most of the time, a primary secondary pumping system will allow us to pump at some reduced pumping load and save a tremendous amount of energy on the larger motor. The advantage here is this. Most boilers operate best with constant flow rates through them. In other words, if the boiler is on, we have a pump on, producing 100% of the flow rate. But what the primary secondary system does, it allows a small pump to pump through the boiler at a constant rate and a very large pump to operate at a variable rate and save the most amount of energy that we can, so that we can satisfy the loads at a variable volume and save pumping energy while we pump through the boilers in a constant volume system and operate the boilers that we want, but use as little energy as necessary there as well. In other words, these constant volume pumps are only on when the boiler is on. Now, I realize I drew a very, very simple system here, and most of the time, you're going to have more than 2 boilers, especially if you're using high efficiency boilers. Personal preference, and for your final project, I want you to use no less than 2 boilers. Consider using 3. See how it falls out with the whole total capacity versus individual capacity of the boilers that you're picking. But I've used as many as 9 2 million BTU per hour boilers in a row for a very, very large building. And the advantage is this. This lets us use these high efficiency boilers with lots of redundant backup. In other words, we can lose one for maintenance, or we can lose one for a breakdown that needs repair, and we don't significantly cripple our boiler plant. Remember, these are high efficiency if they're condensing, which means they're going to require a lot of maintenance and a lot of repair. Having multiples of them ensures the greatest plant reliability while keeping the high efficiency system operating. All right, if you have any questions on primary, secondary pumping, please let me know. And the last part that I want to talk about, we're going to switch gears slightly, and I'm going to show you the way I have it drawn here is in a direct return configuration. In other words, the first coil on the supply is also the first on the return. Now, the downside of this piping arrangement is that the water available at coil 1, the pressure available at coil 1 is much greater than the one all the way down at the end. In other words, this might require a significant amount of balancing and adjusting to get these flow rates equal. Let's say that we had exactly the same flow rate through all 4 coils without any adjustment. If we just opened all 4 of those valves all the way open, coil 1 would get a whole lot more flow rate than coil 4. And the way that we would have to overcome that is by adding balancing valves to each one of these to increase the pressure loss through the first loop so that they would be more evenly balanced. This requires quite a bit of time and effort and is kind of difficult to get balanced ideally. A better pipe layout would be this, the reverse return. The reverse return system, notice what we did here. It's a simple change in direction on the heating water return, but now the first coil on the supply pipe is the last one on the return pipe. And hydraulically speaking, the total distance out and back for each of these coils in pipe should be approximately the same. This is called a self-balancing system or a naturally balanced system. It's not exact. Obviously, you're not going to have exactly the same pressure loss in every loop, but it's a lot closer than the direct return system. This is a lot easier to balance and a lot easier to operate evenly between coils. However, depending on the layout of your building, this might result in more total length of pipe. Maybe. It depends on your building. If your building is like in the shape of a circle or a square, in other words, it naturally lends itself to a loop, this might not add any piping. However, if you have long branches or wings of a bunch of individual parts of the building, this could end up being very difficult to do. It might not be practical for every loop. So these are kind of oversimplifications, but enough to get the understanding. The big point I want you to understand here is, first, understand how primary secondary pumping works, and then understand that with that we can either pump the return in either a direct return or a reverse return, and that has to do with making the balancing easier for the loads. All right, we are going to pause here, and next time I'm going to talk about pump curves. All right, so we're going to pause here, and thank you for listening.